Hello class, this is Dr. Ben. We're going to work on this end of chapter style problem that comes out of chapter 4 that deals with the topic of kinematics. And if you read the problem, you see that we have an object, this airplane that is taking off, and this appears to be a problem, which means that we're going to have 2 points of interest when we eventually go to solve it. But before we do that, the authors ask us to draw a motion diagram for this, and so it looks like we want to just draw a series of dots equally spaced in time in which the spacing increases because this plane is accelerating when it takes off. So if we start with a dot right there and a second dot right there, then we want to draw dots that are further apart. And if I switch to a different color to represent the velocity vectors, make the line a little bigger. Here's the velocity arrows, they're getting longer, and the acceleration would also point to the right. So that's going to represent the motion diagram. So in order to solve the numerical part of the problem, we're going to need to do a pictorial representation. So let's take a coordinate system that is along the x-axis. Let's call that our origin, and we'll put point number 1 at the origin, and we'll put point number 2 to the right of the origin, and so that'll be where the airplane is when it takes off. And so for point number 1, we would have the coordinates x1, v1, and t1. And for point number 2, we would have x2, v2, and t2. Alright, and between those 2 points there'll be an acceleration that points to the right, and you can see that we've got the origin to be at the position of the initial velocity. So we can go ahead and make our table of what we know and what we want to find. So in this coordinate system, the value of x1 is equal to 0. The value of v1 is equal to 0, and we can start our experiment at t1 equals 0. Alright, x2 is one of the things that we want to find. We also know the takeoff speed, so that would be the value of v2, which is 70 meters per second. And we know that the acceleration in this problem is 2.6 meters per second squared. So let's write down what we want to find. And in part B it says the time, so that's going to be the value of t2. And then what is the length of the runway? That would be the value of x2. Alright, so let's move the paper up a little bit so we've got some more room to work, and we'll figure out which of the kinematic equations that are at the top there we're going to be able to use. First of all, to find the time, and then second of all, to find the final position. So, alright, moving this up a little bit. Alright, so if we want to find the time, we need to use one of the equations that has the time. So we know the velocity to begin with, the velocity to end with, and the acceleration. So the equation that says the final velocity equals the original velocity plus the acceleration times the time would be the one that works for us. And so in this problem we would have 70 meters per second equals 0 plus 2.6 times just t2, because we set t1 equal to 0. So therefore t2 would equal 70 divided by 2.6. So if I get my calculator out, 70 divided by 2.6 equals roughly 27 seconds. So that's going to be the answer to the first part. Alright, the second part, we actually can use either of the remaining equations because now we know what the time is. if we use the equation for how the position changes, then we would say that x2 is equal to x1 plus v1 times t2 minus t1 plus 1/2 a times t2 minus t1 quantity squared. Alright, and we know all the numbers that are on the right-hand side of that expression. So the original position is 0, the original velocity is 0, the plane starts from rest, plus 1/2 times 2.6, and now multiplied by this time that we just found, 27 seconds, and we square that. So 27 squared times 2.6 divided by 2 equals 942 meters. Oh, my calculator just tied. I hope I have that number right. But we can check that our answer has units and significant figures. We don't have too many. Maybe we should only have 2. So maybe that's approximately 940 meters. All right.